Hi, my name is Paige Allen, and today I'll be talking about my Physics 2211 Create Your Own Adventure Lab 5, and I chose to analyze the impossible trampoline. So this is today's agenda. I'll be going over the introduction, some physics background, my codes, potential errors along that code, and then the conclusion and another concept question. So the purpose of this lab was to examine the motion of Christopher Hamill and determine whether or not he was defying the energy principle. On the right hand side, you can see the video that was chosen, and it appears as though he is bouncing on a trampoline, but he's also touching the wall. So for this system, we have the man, the earth, and the trampoline, but then in the environment, we have air and the wall. These will not be considered in the code, however, and the program that I had used was GlowScript and Tracker. The main principles that we used in this lab was the energy conservation principle, which basically states that the summation of all of the energies should be equivalent to the total energy in the system. In this lab, since we have the spring potential energy, the kinetic potential energy, and the gravitational potential energy, those three will be what compromise the total energy found in this system. And then on the right hand side, we have Newton's second law of motion with the velocity update formula and the position update formula. These will be used to be able to calculate position changes in the y direction and energy graphs to determine whether or not the energy principle is being defined. Some initials that were found were based on approximations that I had found. So based on what I found online, his mass could be around 72 kilograms. In a normal sports rectangular trampoline, there's about 144 springs in that, each being a length of 10 inches. To be able to find the spring constant, I used F equals K delta X, so that would be the spring force, and I rearranged the equation to be able to find what the spring stiffness would be. Here, since we are only analyzing gravity as one of the gravity and the spring as the only y direction forces, we could say that the spring constant is equal to the force of gravity divided by the displacement of the springs times the number of springs in that trampoline. So during our calculations, I was able to find the point at which Christoph hits the trampoline to the lowest point that he is in within the trampoline, and that would actually be equal to the max displacement found. And I was able to find that it is approximately 1.4 meters. So those were written into our code, as well as the initial position that was found with the tracker. And then on the bottom left, we have all of our initial energies listed. So that would be the spring, the kinetic, and the gravitational potential, and then the summation of the total energy. On the right-hand side, we have a code that is able to help us determine these energy graphs listed, which would be based on that energy principle prior, and we also have the position and velocity update formulas listed. So this was the results from our graphs. The x direction on the top left-hand side doesn't matter as much, but that does indicate that he is moving along more than the y-axis, and there is some discrepancies there. However, we don't care about that for this lab, and we are only focusing on the y position, which seems to show oscillating motion. However, as you can see, each of the peaks within those four major peaks that you are able to see, it seems to be slightly decreasing over time, indicating that there might be some energy loss as he is going up and down that trampoline. This is further supported on the right-hand side where we can see our computational model. Delta E has a major negative spike, indicating that there was some negative energy put in or that was work done by the system instead, which could have been related to when he was hitting the contact of the wall. And we can see that the model and the experimental data relatively show about the same linear graph, except that the experimental data has a much higher peak compared to the model prediction. However, the same trend line goes that there was some energy loss over time. The reason why it might be greater than that is probably due to drag force. So some potential errors and limitations could be that there were calibration issues, air resistance was not considered, which is what we were talking about as the experimental data at a much larger peak. Some initial values had to be estimated based on some research values, such as the number of springs, the length of those springs, Christoph's mass, and then we had GlowScript reading errors that could have happened, but based on my code, I believe that there were very little errors made. So is the energy principle satisfied? There are moments in which negative energy was shown, which indicates that work was done by the system, and that system was probably having contact with the wall at those moments. All other moments appear to remain relatively constant around that zero line, which is true for the energy principle and tells us that the situation was not isolated. Otherwise, if it was, the energy principle would be conserved and so forth. So while it is relatively conserved over time, there are those moments that show that it was not isolated. However, the energy principle still remains true, as in that the total energy is equal to the work done by the system and by external factors, hence why there is negative energy at those moments. A question I had in mind was, what if we tracked Christoph as the point particle? And in that case, the system would only be Christoph, and the external surroundings would be that wall, air, earth, and the spring. So only translational kinetic energy would be tracked, and it would be less accurate since most of the changes in energy would be done by the environment and not by Christoph. So it would be a lot harder to see these changes.